who's a joint PhD student between me and Emmanuel. So, and he's part that's done all sorts of, actually, you'll just hear about one little slice today, but he's done all sorts of very cool stuff. Like, for example, he's done a ton of stuff on CBX pi. So if you get on the wrong side of park, you'll never solve a convex problem. So, that I can guarantee you. He's done all sorts of very cool stuff, ranging from sharpening bounds in the 6th and higher digits for Don Knuth on a problem. Is that about right?
Yep.
Yeah. Let's see. And he actually worked very hard in the graduate student union, which I personally think is awesome. So,
thank you.
Good. But we're not going to hear about that today.
No.
Also, I think I'm probably not supposed to say that, but anyway.
You're allowed to, I think.
Yeah. All right.
I think there's one more person. We saved you a seat right in front, Don.
Oh, it's Don. Here.
Shared right in front.
Right here.
There's a.
ये कर सकता है उसमें से इसमें एयर ड्रॉप से बचा कुछ
Thank you all for coming today. I really appreciate it.
एयर ड्रॉप में वो नहीं दिखेगा ऐसा मतलब
Apple device okay, so if you're on Zoom and you can't hear me, please say something in chat. There's somebody monitoring the chat and who will let us know if something's wrong. But let's get started. So the kind of first question. Hang on, somebody needs to be muted. Let me give you permission to mute them. Sorry, give me 1 second to make a co-host. You should be able to unmute.
Can I go to the library? Yeah, of course. Thank you.
Okay. Back to my slides. All right. Sorry. Back to this. So the kind of first question to kind of answer today is when prediction started as a field, and we asked the first question of how do I predict something from data? The first predictor came about, and they had a model, and they presented it to the world and said to the world, "Look, believe me, I can predict the future." And the rest of the world looked at them and said, "Why should we believe you?" And they responded with, "Well, it worked on the data which I trained on." And everyone laughed and ignored them, and prediction got set back by 5 years because of this foolish exchange. And so as time went on, the people in the prediction designing predictors started trying to get fancier and fancier with the means with which they convinced people to actually believe them, to trust their predictors. And kind of the golden standard was they would just set aside data and only show on that data that they worked. And then people would trust their data because it worked on data they hadn't trained on. But that's, a waste of information. You could have trained on that data instead. So this talk answers the question, how do we trust our predictors without wasting data, without setting any data aside for training, for testing? And instead, if we train on all our data, how do we trust it? All right. So that's the social kind of dinner party explanation. Now for the more precise explanation. So we're going to be given training data, ordered pairs xi, yi. For most of this talk, we're going to be in the random x setting. So x is going to be drawn from some distribution. At the end, we're going to move on to talking about fixed x setting where x is known and has a single quantity across time. But for now, we're going to say we have training data xi, yi, drawn from some distributions. And there's some relationship between xi and yi. We're going to be fitting an estimator, MuPat, that uses information about x to predict y. And we want to understand the prediction error, which is the expected loss of our estimator on unknown data. So what would happen if we were able to see the future? How wrong do we expect to be when we can check how we did in the future? And so it's on unknown data. L is any arbitrary loss function. We're going to assume it's differentiable. We're going to assume one argument is convex, kind of some standard assumptions. But if you're having trouble visualizing what a loss function looks like, y minus mu entry squared is a nice, simple, straightforward loss function that you can visualize. We're also going to assume for this talk that this is a generalized linear model. basically that there's some unknown set of parameters, and the x times those parameters plus some noise distribution where epsilon is drawn IID from some distribution and then some function of that is what we get. So for example, this allows us to describe Bernoulli variables where we might have to be predicting the probability of some event, and then it's being rounded up or down based off of f. And so that's the generalized linear model we're drawing from, and we're assuming is kind of the model. Okay, we're also going to make one more assumption, which is our estimators are given by convex optimization. So our estimators are going to take the form f of x transpose beta hat, where beta hat is the argument of some convex loss function. So here we're making assumptions on L. So we're assuming L is convex. We're also going to assume L is twice differentiable, and we're going to assume R is convex. If you're a real stickler for details, we're assuming R is convex, closed, and proper, but I didn't want to write that down because then somebody might ask me what proper means. If you have to find out what proper means, you're doing something wrong. Okay. And so those are kind of our assumptions on the model that we're training from. And, you know, optimization problems are a powerful class of models. They're the basis of classical machine learning. Neural networks are well approximated by them according to Mert's work. And in general, we see them as the kind of tractable, a class of tractable and globally solvable problems. So we quite like them for that reason. So in this talk, we're going to cover two fast algorithms for doing prediction error estimation. In the random X setting, we're going to talk about RANDALO, which is called randomized approximate leave one out. And in the fixed X setting with Gaussian noise or sub-Gaussian noise, we're going to talk about sure CR, which is signs and bias first estimate for convex regularized problems. Both algorithms are going to be randomized, but they're still going to show that they're more accurate than the alternatives. It's better to randomize our computation than it is to do anything else. And we also have open source Python implementations for both algorithms, and we'll talk briefly at the end about the APIs and how nice and easy it is to deploy in your research. So use my papers and cite me. But obviously, taking a quick step back, you know, this is a PhD defense in its entirety and not just these particular projects. So I wanted to take a moment and talk about all the work that I did here, starting with the n-Queen's constant work with Don, and most recently working on a GPU accelerated conic optimization solver. And so I've done a lot of work, and we're just focusing on two of these papers today, the RANDALO paper and the SureCR paper. Okay. Now for an outline for the whole talk. We're going to talk about prediction error estimates. They're going to be both, some of them you guys will know, some of them you won't. One of them you probably won't. And then we're going to talk about differentiable convex optimization. We're going to talk about how to understand information about how a convex optimization model is fit and how much we can trust how well it's fit. And we're going to use that in order to then do randomized diagonal estimation, which will make some of the prediction error estimates we're going to talk about in the beginning tractable. And once those are tractable and we've got the kind of randomized diagonal estimation, we're going to hard pivot. And we're going to talk about prediction error estimates in the fixed X setting. So in the setting where you don't have exchangeability and where you can't, and you don't have a lot of training data. And so from that setting, we'll talk about randomized trace estimation, and that'll give us sure CR. Okay, getting started. So the easiest way to do prediction error estimation is data splitting. You split your data, put 70% of it for training, put 30% of it for testing. It works great when your data is exchangeable. It's the gold standard of accuracy because there's no bias, there's no anything, it's perfect. So a bit more formally written out, we say we're splitting our data into two parts, one of NC, one of N minus NC. We're only training on the first part of the data, then we're evaluating a nice straightforward plug-in estimator for the expectation. Central limit theorem and strong law of large numbers guarantees convergence. Everything is well behaved. What are the downsides of this? Well, there's kind of two downsides. The first one is we're wasting training data. We're not training on all of our data, and that's a shame. It'd be nice to train on all of it. And so some people have a solution to this, and that solution is they're going to use train test split. They're going to pick all their hyperparameters. Then they're going to go back and they're going to refit their model on the whole data set. Well, it turns out that's biased in high dimensions. So in high dimensional statistics, that's going to have bias, introduce bias, kind of similar to how CV is biased in high dimensional regimes. So that's the loss there. You're going to end up with bias if you try and do the just fitting hyperparameters and then going back and training on everything. Okay, so what are some ways to try and address this? Well, this doesn't address the bias issue, but it does address the not using all your data issue. We have k-fold cross-validation. And so this is the real-world workhorse for prediction error estimates. It's what the whole world kind of runs on. In basically any setting, people will try and figure out a way to get CV to look reasonable, even in time series data, which always amazes me. And in this setting, again, we're assuming exchangeability of data. The time series people love to use it anyways. And the entire data set, so we have the entire data set, we split it into folds, we split it into small parts, and then we use one part for testing, and we fit our model on the rest. Then we go to the next part, and we use all the data for testing, except for one part, we use all the data for training, except for one part, which we use for testing, and we do that for each fold of the data. So here it is a bit more precisely stated. So we split the data into k parts, and then we construct partial estimates of the prediction error, and then we combine all three at the end. Or sorry, all k at the end for KCV. So 5CV, 3CV, 10CV, all very popular. Here's the problem though. When k is fixed, so in the setting where you have a small k and your sample size is going to infinity and your parameters are going to infinity, so in the high dimensional setting, then KCV is inconsistent. And that's a shame, because it means you pick the wrong hyperparameter some of the time, or you pick the wrong model and you don't actually know your prediction error, which is not what we want. So the easiest way to fix that is you don't use fixed k. As long as k is growing with your sample size, you're all set. So we have leave one out, where you take NCV, where you split your data into n folds, and you're only using one sample at a time. And we can think of it as an equivalent formulation is kind of this argument, where we have our prediction error loss. L is the difference between these two variables, and then we're each one of these squiggly y minus i's is given by training the data excluding a single data point. And so once we're excluding a single data point, and then the asymptotics start behaving nicely, it's the folds are small and they shrink as we get more and more data. And so everything behaves well, everything's perfect, everyone's happy. Why don't we use this in the real world? Well, it's really expensive. You're either going to be paying in a lot of parallelism, you're going to be paying in a lot of memory, or you're going to be paying in a lot of compute or some subset thereof. And so it's not free and it's pretty expensive. And so you can't actually use it a lot of the time. So what do we do instead? Well, the next easiest thing is let's approximate it. And so we're going to introduce approximate leave one out. And this has been well studied in the literature. And the basic idea is you look at these optimization problems and you imagine that you are taking a single Newton step, starting at the solution to the whole problem. You take a single Newton step towards optimizing each of these arguments. And because you're doing one Newton step, you're getting pretty good accuracy. I mean, a Newton step's pretty good. We once were able to find in 10 million dimensions with 10 Newton steps, we were able to find a constant out to 7 digits, right? Like a Newton step is quite good. And we take our small Newton steps and we get closer and closer to the to our target, but we only do one Newton step, right? And so because of that, we're approximating leave one out. If we did all the Newton steps we needed, we would have exactly leave one out, but we're only taking one, so we're doing approximately one out. And with approximately one out, it turns out that it has this very nice expression where we can view it as the original prediction plus a corrector term. And that corrector term is is the result of the Newton step and is the result of the approximately one out. And so we're going to highlight this quantity right here, JII over 1 minus JII, and I'm actually going to write it on the board. Hey, I forgot to test that my markers work. We're going to be thinking about this quantity a lot as we go through this talk. And so what is J? J is the derivative of the training predictions with respect to the training labels. And so that's a huge matrix, right? If I'm talking about a setting where I have 100,000 data points, that's 100,000 by 100,000 point matrix. Turns out that it's very rarely sparse. It's oftentimes a dense matrix. And so we're looking at a massive Rn by n matrix that is way too big to form, way too big to store. And so we have a problem there. But for now, let's pretend we don't have a problem. We're going to pretend we don't have a problem for a bit, and we're going to just do everything as if it's going to work. And then we'll fix it at the end. Sound like a plan? Awesome. Oh yeah, there is another way to interpret approximately one out. You can view this term as a corrector, where you're scaling up or down the residuals based off the quantity of this term. And so it turns out that the matrix J is guaranteed to have diagonal entries inside of 0, 1. And so this will always be between 0, 1. And so it just represents a scale of how much we need to scale up or down the size of the residuals. And this should make some intuitive sense that this diagonal quantity is what we need. Because it's saying, if we're really close to 1, right? If I am predicting that the training prediction is going to change a lot with a small change in the training label, then that means this should be close to 1, and this quantity goes to near infinity, which makes sense because if I'm learning data, I would expect to be learning from many data points, not just a single data point, right? So we're it makes some intuitive sense that this looking at the diagonal is the right thing to do, and especially kind of this form is the right form for how we're looking at the diagonal. All right, so we have convex optimization problems that are giving us our estimators, and we need to look at how we're training. We need to differentiate the fitting process of the convex optimization. So now we're going to turn to the next topic of this defense, differentiable convex optimization. So approximate leave one out depends on the Jacobian of the training process, as we just discussed. And so in this section, we're going to talk about ways to differentiate solving a convex optimization problem. We're going to talk about 2 of them. One of them scales to really big problems really well, and scales to some really weird kind of differentiation, things we can differentiate, and some strange regularizers, and we'll talk about that. The other one is really nice, efficient, elegant, and easy to explain. And so we're going to talk about that one first. And all we're going to try and do for now is compute a single vector Jacobian product. So we're going to imagine that we can form these oracles, these Z transpose J or JZ oracles that are doing a single vector multiply with the Jacobian. So with these oracles, we would need n queries to evaluate ALO. That sounds like a lot. Randomization will fix that later. Okay. So here's the core kind of challenge. Let's write out the chain rule. Let's work out where the derivatives go. So I have Z transpose J. I end up with Z transpose d mu hat dy, right? That's my definition of J. And then my d mu hat dy, we're pretending F is the identity just for simplicity, but you can add an F term in the middle if you'd like. Then we have X times d dy of the argument. And this, I don't know how to differentiate. If I pulled out an elementary calculus student and I asked them to differentiate this, they'd probably get lost. So this is where the computational challenge of the problem is. This is where the analytic challenge of the problem is. So that's what we're trying to find. Differentiating through the argument. And so we're kind of lucky that we actually have some information about kind of the differential properties of an optimization problem that are given by the optimality conditions of the optimization problem. And so because we have the optimality conditions, we know that these are going to satisfy this nice recurrence, or this nice differential equation. And if it satisfies this, well, we can implicitly differentiate this expression, and then we get a nice expression that includes the quantity we're interested in. And now we just need to solve this equation. And so it turns out that for some regularizers, it's easy to solve this equation. For ridge regression and lasso, we have nice, clean expressions that fit on a slide, which is awesome. We love when things fit on slides. We also have we have some very messy expressions for cases which don't fit on slides, but there are a few other analytic closed forms expressions. And so ridge has a nice form that perhaps some of you recognize, the kind of projection matrix like structure. Lasso is also a projection matrix, but now only on the selected columns. So we're getting some intuition for it, hopefully. But it turns out we want something more generic. And the reason we want this is because this is not a good enough. These are not enough. These are not all the regularizers we want to deal with. We want to have a much more general expression that works for many more regularizers. And so we end up, for example, you can consider the first differences regularized least squares. If we imagine that our X has some order, and we expect that our B should be piecewise a constant, then we'd expect it to be sparse in the first differences. And if it's going to be sparse in the first differences, then that means we want to regularize for that. And there's no easy to write down expression for the Jacobian of this. There are some tricks to computing it with a lasso solver, but the Jacobian starts getting quite messy and it's hard to describe. So we want something more generic that applies generally. And so we ended up coming up with this theorem that allows us to decompose the regularizer into a sum of simpler regularizers. And then we're going to do an analysis on those sums of regularizers. And it works for a lot of very interesting problems. So we were quite happy with the strength of this. So here's the decomposition of R. We're going to decompose R into, first, we're going to gather all of anything that's twice differentiable into the first term, into the R naught term. We're going to ignore it. So forget that any part of it is twice differentiable. And the rest of it is going to be a sum of regularizers that are twice differentiable everywhere, but at one point, but at 0. And without loss of generality, you can let that be any point. But for our purposes, it's going to be at one point, it's non-differentiable. And so this S is going to be locally, and then we're going to assume that which regularizers are at 0, which ones inputs are at 0 is locally constant. This is kind of necessary to ensure differentiability. But you can do a rough approximation even if it's not there, and that'll give you some value. Who knows what that value is, but it'll give you some value. And there's a couple more regularity conditions we described in the paper, but they're pretty gnarly technically, and I think almost always satisfied. I'd be hard pressed to find an example. I haven't been able to find an example where they're not satisfied. So we're skipping them for now. And then in this case, the vector Jacobian products are given by the solution to a QP. And not just any QP, an equality constrained QP. And because there's no inequality constraints, this means that we can solve this QP with a single Newton step, i.e. one linear solve. And we're guaranteed a solution, optimal solution. And so long as the problem is feasible, which it has to be because 0 is feasible. So it's always guaranteed to be feasible, and therefore we can always find the solution with a single linear solve. Okay. And this decomposition, it covers elastic net, it covers group lasso, it covers the LK norm regularized regression of any linear function. It covers them all, and that's been more or less a large family of regularizers that we've been quite happy with working with. The only thing missing are spectral regularizers, where you expect B to take some form of a matrix, and you want to regularize the singular values of the matrix. You want to regularize these singular values of the matrix instead of the entries of the matrix. Okay.
Maybe you can tell people what vector Jacobian products are given by acting star.
What vector Jacobian stars? Yes. So specifically the vector Jacobian products with the fitting process of the original sorry, going back a few slides. Oh, and my slides first. So it's the vector Jacobian products of X beta hat is with the vector Jacobian products that are being given by V star. V star to
Derivative of beta hat.
Yeah, the derivative of beta hat with respect to what?
Right.
The training wheels.
So derivative.
Yes. Derivative of beta hat with respect to the training tables. Yes. Okay. So jumping back to the theorem, the proof is fairly straightforward. As with all straightforward proofs, don't ask me how long it took me to come up with it. But no, so the key insight to the proof is if we just rewrite this expression in separating the terms that are not 0 from the terms that are 0, we can then do a variable substitution that's locally true, locally equivalent of dk equals 0, because that's true locally because of our assumption on S. And then once we get that, we get this expression. This has differentiable constraints and differentiable objectives, which means that we are guaranteed, we satisfy the implicit function theorem with one other technical condition for the paper. We guarantee that the implicit function theorem is satisfied, and then we are guaranteed the derivatives exist, and they're given by the QP. Okay. So that's the core idea of the analytic implicit function theorem method to solve to differentiate the programs, differentiate the optimization problems. But there's another method called unrolling, which scales to really large problems, is easy to GPU accelerate, and works for the spectral regularizers that we were unable to get working with this. So that's the exciting alternative method. And so we're going to talk about that now. So the big idea of unrolling is you solve the optimization problem with an iterative algorithm, and then you do backpropagation through the iterative algorithm. And so that's the big idea. We're basically creating a neural network, whose each layer is one layer of an iterative algorithm, and then we're just doing backpropagation on that neural network. Also, for simplicity in this subsection, we're going to let L equal the L2 norm squared. This is not necessary, but boy, does it make the equations easier to write. So you guys are all going to be subjected to that simplifier. Okay. Also for simplicity in this section, we're going to focus only on iterative algorithms that involve proximal operators. Proximal operators are nice and well behaved, and we've done some cool work on spectral proximal operators that we'll talk about in a second, and that allows this to behave really well. And so a proximal operator is nothing more than a regularizer plus an error norm squared error term being minimized. And so these are nice. They're one Lipschitz functions, which means that their Rademacher's theorem guarantees that they're differentiable almost everywhere. And so that's really fun. That's perfect, right? Because we need to differentiate them all. And you know, what are the chances that we end up somewhere that it's not almost ever differentiable? And the answer is extremely likely, because we are not randomly sampling with respect to the Lebesgue measure the point that we are differentiating at. We are actually following the iterative algorithm's trajectory, and the iterative algorithm tends to be polling the matrix. For example, if I'm doing nuclear norm regularization, then I'm trying to create sparse singular values. And to get sparse singular values, that means we're pulling towards where the proximal operators are not differentiable, because it's a set of measure 0 where the matrices that have singular value 0. And so because we end up pulling towards those non-zero points, we end up encountering some really nasty numerical issues that pop up. And so what you have to do instead of evaluating the spectral regularized, so instead of just evaluating the proximal operator's derivative, we instead find a continuous function whose a continuous function that is equal everywhere where the proximal operator is differentiable to the proximal operator, but which is differentiable. And this function exists. It was a surprise to me that it exists, but it does exist, and you can work out its derivative we worked out its derivative in the appendix of the paper. And if you're a huge fan of messy algebra, I highly recommend that appendix. And if you enjoy just trusting me and not reading messy algebra, you can do that too. But it has worked numerically, so I think it's actually correct. Okay. Moving on back to kind of unrolling, we're going to do one example unrolling problem using ADMM as our example first order method, and that will hopefully give us a sense of how the unrolling works, and it applies to all sorts of other operators. You can do it on Fista, you can do it on Ista if you really want to waste your time, and there's lots of options. Okay, so ADMM is given by a nice simple recurrence when formulated in the right way, and this recurrence is basically you take in a u and a z, you compute a b, you compute zk, and then you update u with that information. This is nice. This is extremely nice because we only have two state variables, u and z, that we have to store, which is ideal because we have to store the value of the iterates for each iteration. That tends to take far fewer iterations than the size of your data matrix X. So that's actually not a huge problem memory-wise. But obviously, if you're in a regime where your X is extremely sparse, sometimes you'll have problems. Yeah, so we determine the number of iterations we need to run via some stopping criteria that looks at B and Z. And then we just take, after we find ADMM iterates, we say, right, if it takes 200 iterations to get to a stopping point, we say, all right, after 200 iterations, this function is going to be approximately and hopefully locally equal to our true solver that's able to get to the optimal point with infinite iterations, right? So our hope is that once we've converged, we're close to the true value, and its derivative is also close to the true value. Okay, Some of you are probably scared by the matrix inversion here. You know better than to look at a matrix inversion and think that that's tractable. Sometimes X is really well structured, and that's really easy and this matrix inversion is really easy to compute. Sometimes we can do a simple factorization of X, or we can apply randomized linear algebra in order to do this matrix inversion where we just have to sketch X once and then apply some cool stuff like Nystrom PCG to do this inversion. And this is kind of pretty much the perfect setting for kind of randomized methods like Nystrom PCG because it's data fitting where X transpose X is going to be relatively well behaved and not adversarial, and we can take rho to be pretty large if necessary for numerical purposes because rho is arbitrary. It just needs to be non-zero. Okay. Yeah, that's my thought there. So let's take a step back. We can view these ADMM iterations as a function mapping updates of Z and U and Y into the next Z and U. And once we do that, we can just implicitly differentiate this update equation, and we get a nice simple recurrence that after we complete D iterations, we just have to backsolve. Starting from here, we just have to backsolve, and we're able to compute the ADMM, unrolled ADMM's derivative. All right. And that's the core idea of unrolling with one example worked out. Okay. Now we got to move on to the fun parts of the talk, which is the randomized diagonal estimation. And this is where I think it starts getting much more interesting and novel. All right, so our goal is to compute ALO fast. So far, we have described a method that requires n QP solves in order to compute ALO. That is hopefully sounds way too expensive to you. At that point, you might as well just leave one out itself. Why are we trying to approximate? QP solve is going to be roughly on the order of solving a regularized problem anyways. Well, it turns out we don't need all n QP solves in order to get compute ALO accurately, courtesy of randomized linear algebra. And so we're going to do random diagonal estimation, where we estimate just the diagonal of a matrix with far fewer queries to our oracle than n. Specifically, we found that experimentally 50 works. Just 50. No scale. 50. Okay. Yeah. So randomized methods require much less use of the oracles. So here's the core idea behind randomized diagonal estimation. There is this very simple expression where if we have Z be a Rademacher random be a vector whose entries are Rademacher random variables. For those of you unfamiliar with Rademacher random variables, it's either plus or minus 1 with equal probability. It's a fancy name, not too complicated, hopefully. And so there's a nice expression where if you take the entry-wise product of a vector of Rademacher variables times a matrix vector product of times one query to the oracle, then in expectation, that's equal to the diagonal of J. So all we need to do is apply the central limit theorem, and we get what's called the BKS estimator, which is just using the central limit theorem, we're guaranteed square root m convergence, and we get nice performance. That's all well and good, except as we all hopefully know, the central limit theorem doesn't guarantee. So right now we know the diagonals of J have to be between 0 and 1. We know they have to be between 0 and 1. And central limit theorem makes no guarantees that it will actually satisfy being between 0 and 1. And so we come back to this expression and we ask ourselves, what happens if we get a negative output? Well, this makes no sense. This is supposed to be a quantity that measures how overfit something is, and it doesn't have any meaning what does a negative overfit mean? I don't know. Similarly, if we get something over 1, then the sign on the denominator flips, and while it should be infinity, it's actually going to start decreasing, and it, again, makes no sense. So instead of just taking the output of the BKS estimator directly, we're going to try and make it a little bit more stable or numerically, along with imposing a constraint on 0, 1, by taking a Gaussian. We're going to fit a Gaussian with, so BKS estimator also gives us a variance estimate, right? It gives us the mean estimate, and it gives us a variance estimate. So we're going to use the mean estimate and the variance estimate to form a Gaussian around the BKS estimate. And then we're just going to truncate that Gaussian to 0, 1 and take the mean of that Gaussian. This is nice both numerically because it does a little bit of regularization pulling us away from 0 and 1, which decreases the chance that we end up with like, if we end up with 0.999999 here, then our floating point arithmetic starts getting messy. So that regularization really kind of helps stabilize that, especially because in our experience, most of the times where you get the many nines, that's probably just BKS being an overestimate, more so than naturally data being that wildly overfit. Though obviously at some points it is wildly overfit, and in that case, the variance estimate is probably going to be very small anyways, because the structure of the J matrix guarantees kind of low variance in this case where the diagonal is very close to 1. Okay, and so we're going to use that to create our estimator, which we're going to call diag hat J. And this is going to give us an algorithm, our first algorithm of the day, BKS ALO. And so the basic idea is we construct the oracle via the theorem given the solutions. We're going to find the BKS estimate and the variance estimate. We're going to find the truncated mean of Gaussians, and then we're going to evaluate it. And we're going to find the PE hat is the corrected value where we just did a plug-in estimate of diag hat JI into the JII values. That's all well and good. So there's a problem here. And here's kind of the core of the problem. This is a not quite unbiased, but it's effectively an unbiased estimate of the diagonal. This is a nonlinearity. Sadly, expectations and nonlinearities don't pass through each other. It'd be really nice if they did, but for some reason they don't. And so we end up being biased, and it turns out we always end up being biased upwards for a few reasons. But here's kind of the intuition for one of them. The first idea is why I hat is at the parameters, is at some function of the parameters plus some noise that has known or unknown variance, mu squared. And then the BKS estimate is adding an estimation error to that prediction yi tilde, which is of size epsilon I, and it's going to have some variance sigma I squared over m, where that sigma I is actually the BKS variance estimate. And so what we end up with is we end up biased upwards because we're actually evaluating the loss function not at nu squared, but at nu squared plus sigma squared over m. And most loss functions, frankly, you have a bad loss function if it doesn't have this property, most loss functions increase in value as the size of the noise in your system of your estimation problem is getting larger, right? Makes some intuitive sense, hopefully. If it's noisier, you expect your loss to be worse. And so we end up always sampling and oversampling the point when we do this corrector. So we end up with an overestimate, which is a shame. It'd be nice if we could get an estimate that wasn't always biased upwards. That was the whole thing we were beating up on CV for being biased. And so what we're going to do is we're going to apply a debiasing step, which I like to call the Taylor series make everything better approach. Okay, so this is going to get very notation heavy, so we're going to define a few new functions. So G of D is basically just our expected loss, or our prediction error estimate. It's our prediction error estimate as a function of the diagonal. And so F, looks like this, but it could be any function, and there's going to be some other terms in front that represent kind of scaling terms, etc. But for all intents and purposes, this is our prediction error estimate in BKS ALO with respect to the D as the diagonal. So now we're going to condition on the samples. Once we've conditioned on the samples, this is a function of just the sample size, m. It's a scalar function of just the sample size m. And so as we pick our different m values, we could evaluate this function at different locations, and it's going to have some curve and some plot. And we really care about the asymptotic behavior because we know it's going to be correct by the delta rule. We know it's going to be correct when m is infinity. So what we end up doing is we instead imagine another function, which we call h of 1 over m, which is continuous, right? We're assuming h is continuous, and we're guaranteed this function exists because you can just do any sync interpolation and you're guaranteed it'll behave nicely. And so we have H over 1 over M, which is equal to G of diag hat J, so sample size N. H of 1 over M is a deterministic function conditioned on the samples, that converges to ALO as its argument goes to 0, right? As 1 over M goes to 0, then H is going to converge to ALO. So our goal is just to find the y-intercept of H. And it turns out, for reasons we get into in the paper, and I'm going to skip right now, it turns out that H is about linear. It's mostly a linear function, which is very nice because it means we can do a single sketch of the Jacobian J, where we multiply it with a big random matrix, and we get our sketch. And then we're going to subsample columns in order to create samples of different sizes. And those samples of different sizes, we can plot them on a line. And sure enough, we find that the y-intercept is a much more accurate estimator than any of our actual samples. And so we do this. So in this plot, we do this for m equals 30 and m equals 100. We didn't do m equals 50, which is our normal number, just because it makes it harder to see the two of them. And I wanted to capture the clustering, right? So we have errors in the m equals 30 case that are roughly on the order of about half 0.05 or 0.005, I should say. And that is smaller in error than even when we use 100 sample points compared to BKSLO. And when we use 100 sample points, we find that our y-intercept is exactly at the right point, or at least within a few pixels of it. And this generalized to all the problems we tested, and it worked phenomenally well. So kind of describing that in a bit more mathematically with a little less plots and less me hand waving, which hopefully is easier to follow. So we're subsampling the samples. So first we sketch the matrix by computing a bunch of J transpose Z's. Then we subsample that in order to evaluate H at different points. And then because we assume H has a Taylor expansion, which is an assumption that prediction error is continuous at nu squared, which it probably is, then we learn the coefficients of H's Taylor expansion from the subsamples in order to find H of 0. And that gives us a much more accurate estimate of ALO than the BKS ALO. Also, we plotted this in order to see how quickly it converged. So here is the true, right? Here, this black line is the true ALO. The blue dashed line is BKS ALO, and it takes quite a while for it to converge, and doesn't even fully converge at 300 sample points. Meanwhile, with just 50, we're within the same error that we would get with 300 points, and within 100, we're pretty much indistinguishable from the one with Rand ALO. So the debiasing worked really well in the test problems. Okay. Here is, so now we're going to put everything together and we're going to look at what Rand ALO looks like. I'm going a bit slow, actually. So hopefully people don't mind. So we're going to construct the oracle. We're then going to take the iterates over subsets of different sizes. We're going to sample random subsets of those sizes. We're going to compute the subset statistics and find the diagonal estimate for that subset. We're going to estimate the leave one out prediction. We're then going to compute the prediction error estimate for those subsets. And then we're going to regress, finally, after we've done that loop a bunch of times, we're going to regress that onto our linear expansion, with 1 over m prime as our variable x. And then we're just going to use that as our prediction error estimate, is 0 of that as our prediction estimate. Okay, putting that together, that's our algorithm. Let's see how it does. So here is the plot of Rand ALO, BKS ALO, and CV, along with conditional risk curve. It's a little bit colorful, apologies, but you'll notice that the orange line, which is where CV finds the optimal hyperparameter selected by CV, is over here. The true optimal hyperparameter is here in blue, and Rand ALO ends up much closer to it than CV does. And here's the real benefit. This is the amount of time it took to get every single point on this plot. It took CV between 4 times as long as it took us to train our model, 4 to 5 times as long as it took us to train our model, and that's without actually training the final version of the model. This is just computing the prediction error estimate. In contrast, I took BKS ALO and RAND ALO less than 1.5 times consistently across the entire parameter space to train our model. And this was more than enough for us to say no time flat, and significantly faster than CV. Also, just to beat up on CV a little bit more, in this setting, which to be clear, square matrix data, FLASO is when CV tends to be most biased. The kind of square data matrix is where CV performs worse. So we definitely picked the regime CV struggles in, but it's also, I think, a pretty reasonable regime. The idea that you have about as many sample points as you have parameters, that's a very good place where you really are relying on your shrinkage to be selecting things. And so we think it's a fair place to do competition. And then RAND-ALO selects parameters well. So in this setting, we picked two parameters, lambda equals 10 and lambda equals 15. One of them is better than the other. I believe it's lambda equals 10. Yeah, lambda equals 10 is a better choice than lambda equals 15. CV, and we just ran it repeatedly. We just, we sampled data from the distribution and we just ran it and we said, are we picking the right hyperparameter? Do we pick the right hyperparameter? And how many times? 5CV, 37% of the time, picked the better hyperparameter. BKS ALO, 99% of the time. So this is without debiasing. 99% of the time, pick the right hyperparameter. RAND ALO, we couldn't find a single period where with 50 samples, it picked the wrong hyperparameter. Over the 100, I think we did 100 samples. Okay, I'm apparently unable to connect to a HTTP proxy, and I don't know why I would want that.
Is 10, right?
Yes, correct parameters.
The problem with CV is that you increase dimension, so it wants to regularize too much.
Yeah. CV is trying to over-regularize. Okay. That's it for RAND-ALO. There's a lot more experiments, numerical experiments in the paper. Happy to talk about them in questions. But in the interest of time, we're going to move on to fixed X, the fixed X regime. We're going to do this a little bit faster, partially because you already know how to differentiate convex optimization problems. Okay. So the only prediction error estimate we're going to look at for a fixed X is the Stein's unbiased gross estimate, which applies only to Gaussian data and works pretty well for anything sub-Gaussian. And so there's no exchangeability assumption on the training data. And so you can view, this says EG, you can view this as having a single high-dimensional sample from your distribution. You have one high-dimensional sample from your distribution, and you're preparing, and you want to understand how accurate your predictor is for predicting the mean of that distribution. And we're assuming we know the variance of epsilon, Gaussian with known variance, or at least estimatable variance. Because we don't have an exchangeability assumption, we don't get the free variance estimate of just kind of averaging things together. So known variance is not non-trivial, but it's also not too unreasonable, especially in imaging applications. Okay, and our prediction error estimate is going to be the training loss plus a scaled version of the divergence, i.e. the trace of the Jacobian, where this is the same Jacobian that we're studying as in this previous problem. The training predictions differentiated with respect to the training labels. The training predictions differentiated with respect to the training labels. Okay. So this is a nice simple expression. You'll notice that this is a linear relationship between our prediction error estimate and the value we're trying to estimate, which is nice because we don't have to do any of the debiasing that we had to do last time because we have nice, well-behaved linear expectation. So that's one of the benefits to this approach. So because we need the trace instead of the diagonal, we can do better than just diagonal estimation. And I can talk about why we think this is, yeah, we can talk about more about kind of some of the differences in a moment. And basically the same theorems apply as the diagonal case, but now instead of taking a entry-wise product, we can take a inner product between our Rademacher vector and our oracle query. And the central limit theorem gives us a nice m to the negative 1/2 convergence. That's nice. Turns out we can do better. And so we said, why not do better? So let's do better. And so we're going to use a different estimator called Hutch++. And the basic idea of Hutch++ is that I can, for any orthogonal matrix, you can decompose the trace of the Jacobian into these three terms. The trace of the matrix projected only onto the column space of the matrix. This term, which you'll notice by the rotational invariance properties of the trace, QQ transpose times I minus QQ transpose, guaranteed to be 0. So we get to ignore the middle term. And then this is the trace of the dimensions projected away from the dominant matrix shape. From the matrix projected away from Q, from the column space of Q. So this is nice. And so one way to do, so what we do with this is we try and make Q the dominant dimensions of the matrix J. And what do we mean by dominant dimensions? We mean the eigenvectors associated with the largest eigenvalues of the matrix J. And so those eigenvectors are going to be, they're easy to find by just doing left matrix multiplies, right? If I multiply a matrix by a random vector, its dominant eigenvectors are going to be the largest part of the output. So that's what we do. We use a third of our queries to estimate the dominant eigenvector space. We use a third of our queries to find the trace exactly on the small matrix here. And then we use another third of our queries to run Hutchinson's estimator on the last. And once we do that, we get Hutch++, which is guaranteed to converge at M inverse. So much faster, about quadratically faster. And so putting that all together, we get sure CR, finds a bias Chris estimate for convex regularizers. And in this case, we're describing how to do it with the unrolling. Both algorithms are described in terms of a given oracle, but it's optional. You can swap the oracles between the two of them and it works fine. And so we unroll the iterative algorithm, find mu hat, and form the oracle Z transpose J. Then we apply Hutch++ to find trace J hat. And then we just evaluate that. And we evaluate the prediction error. And it works quite well, courtesy of linearity. And kind of seeing that it works really well, we have some matrix completion problems. So here we're testing it on those nuclear norm regularized problems. So you got to kind of see the numerical accuracy of our continuous extension trick from earlier. And sure enough, the Monte Carlo risk for this problem and the sure CR risk for these problems are indistinguishable across the entire parameter suite. And so that was nice. And it turns out that we kind of ran this in more details. We see about 1% variation total across the entire space. And also on top of that, so some people worried that we're adding extra randomness, right? We're adding this randomness associated with estimating the trace of J, sure, and sure is already a random quantity, right? Because sure is an estimate of data anyways. And so I got asked, well, how do we know that you're not adding so much randomness that it's making the problem worse compared to the underlying sure estimate? So we quantified that. And this is the randomness inherent in sure CR from the trace estimation. This is the randomness inherent to sure. We're not adding much in terms of noise. And the rough summary is we sampled a million matrices, and then we averaged, and we used that to find the Monte Carlo risk, and use that to find the percent of Monte Carlo risk that was kind of inherent in sure. And then we, for each of those matrices, we sampled them 100 times each, or sorry, I think 1,000 times each. I was having a fun day with the cluster and just turning all the numbers up. And for each of those, we averaged their values and saw how much variation there was for a given image sample. And so for each image, we were looking at almost nothing in terms of noise, whereas we were getting this widespread for image to image variation. Lastly, we're going to talk about the open source implementations available for both of these packages. RandALO has a nice modeling layer. It supports arbitrary vector Jacobian oracles, so you can bring your own Jacobian oracle. But if you want us to form the oracle for you, we have a nice modeling layer that's inspired by CVXPy that has some nice features specific to kind of computing these oracles. And then we also have automatic support for some scikit-learn models. It's always just somebody telling me that they want to use it with a new scikit-learn model that gets me to go implement the new ones. So let me know what you're using it with and we'll add support. It probably takes about an hour at most to do that. So just feel free to open a GitHub issue and we'll get it resolved within a day or two. And then SureCR, we support using CVXPy to specify your problems. And we also support we also have all sorts of tools to help you use to form first order unrolled proximal methods. And with that, that's it. Briefly, before we move on to questions, I wanted to take a second to acknowledge some people. In particular, a huge thank you to my advisors, Stephen and Manuel. I would not have been able to get here today without them. They've both taught me a ton in both in writing, in math, culture, in mathematically, and just how to be a productive researcher. And it's been an honor to kind of look up to both of them throughout this time. Thank you to the rest of my committee. I worked with Michael in Berkeley for a summer and for some amount of time after that. We never did finish that paper. I promise I'll get a draft to you soon. I learned a lot about randomized linear algebra. I really would not I would not have been able to have done a talk with as much randomized linear algebra without the time I spent with Michael. Similarly, Madeline's work has been inspiration, especially kind of the early nitrogen PCG work was a real inspiration for me to go down that rabbit hole. And Mert has been much of an encourager of much of my randomization and has had wise advice every time I've asked him about it. So I greatly appreciate it to my whole committee. A huge thank you to the CVXPy team. I know a bunch of you are here virtually, and one or two of you are here in the room. The CVXPy team has been a huge part of my professional development, a huge part of my, I would not have gotten the summer internships I've had without them. I would not be the programmer I am today without them. And it's been a great honor to work with all of them. Love them all dearly. Many co-authors and other collaborators, which I want to appreciate, both Daniel Lejeune, with whom a lot of this the Randy LO work was done. Without his help, it would have been hopeless to get this project done, to be honest with you. And everyone else was really everything. I also want to particularly thank Don for coming today, and also for my first project in grad school was working on the N Queens constant with him, and it was really inspirational to kind of have his encouragement and support as I was finding my footing. I also wanted to say thank you for that. I also want to take a second to thank advisors of the past, Jajit Roy Chowdhury and Catherine McMillan. Without them, I would not be the mathematician or writer I am today. So I'm always appreciative of everyone from back then and throughout my scholarly journey. On a more personal note, I'm largely, a functioning human being, courtesy of my friends and all the support and help they provide. And so I would not be able to get through really anything I try and do without them. So a huge thank you to all of them. Huge thank you to the family across the US who are zoomed in and here in person, who have always been supportive and a huge part of my work. The Bay Area family and my parents' friends who qualify as Bay Area family have always been a huge part of, making sure that I've had more meals courtesy of them than any other group other than my grandmother. And of course, a huge thank you to my brother, parents, and grandparents, maternal grandparents especially, who have always been kind of pushing me and inspiring me and giving me a benchmark to try and surpass, especially Sean on that last part. And yeah, thank you. I think we have time for questions. Yes, Riley?
Could you go to the trace estimation?
Yes.
Maybe, yeah, this slide is a good time. So obviously the trace of a matrix does not depend on whether or not it's symmetric or Hermitian.
Correct.
But like the concept of like estimating a dominant eigenspace, like even just that is sort of supposing that it's a normal operator, like it's going to commute with its adjoint. So like, there is an orthonormal basis of eigenvectors. Like,
So we're assuming, is that true? I mean, you could just say the Jordan canonical form, right? The Jordan canonical form guarantees that you're going to have some matrix of the
Okay.
form Q thing that has the same trace,
okay,
Q transpose.
but then how, I guess,
Not the same, yeah, the same trace. Because
well, yeah, the
yeah.
trace will be the same. I guess it's one of these things where it's like if your matrix isn't normal, then the absolute values of the eigenvalues won't necessarily equal the singular values. And so I'm kind of just wondering how that, like, how many of these of the off-the-shelf estimates for like Hodge
Yeah.
apply to.
So we have a couple of advantages here. First off, the matrices we're studying are the Jacobians tend to be, in most cases, depending on the regularizer, courtesy of the convexity of the regularizer, we do normally have that symmetry.
Oh, okay.
So that's the first.
Out of the question.
That's the first get away with it. So they are normal. So we can set that aside. And even if they weren't normal, in those cases, because I mean it's effectively a second derivative, right? And so second derivatives tend to be symmetric, without outside of weird particularity conditions.
Because the first derivative is coming from the definition of like the beta.
Exactly. Because the first derivative comes from the beta hat, and so the second derivative comes from the y.
I just lost track of that of the derivative. Makes sense.
Fair enough. But on top of that, we're also kind of, I mean, we're still safe, because this equality holds for any orthogonal Q. So where correctness is not a function, we only lose possibly the convergence rate. And that's true. Hodge++ has no proven convergence rate for non-symmetric matrices that I recall. Actually, no.
Or I mean, at least not stated in like.
It's not stated in the original paper. I think Cortinovis might have proved one. Alicia might have proved one. I don't have them memorized.
I mean, I'm good. I'm satisfied.
Okay. Any other questions? Yeah, Aditya.
Could you talk a bit about the motivation in the Randomization theorem for why you chose that particular decomposition of some of these RBs except differential except at one point?
Yeah. So we picked that because I wrote a list of regularizers, and I stared at it, and that was the only property I found that they all had. Is the short answer. And to be clear, they all actually do have that property if you put an asterisk and write on a manifold. And then even the spectral regularizers also qualify that way. So if somebody is an expert in manifolds and wants to talk to me afterwards about how to generalize this, please find me. But that's the short summary. It was the only thing we noticed that they all had in common. And then from there, we've made a proof sketch where we've cheated and used Dirac deltas everywhere. And things behaved well with Dirac deltas everywhere. And we were like, well, that probably means it's correct. And so then we found this proof in trying to formalize the Dirac delta proof. I hope that answers your question. It's basically
Dirac deltas everywhere.
Basically we said, well, what would happen if there was a Dirac delta times a Jacobian or times a PSD matrix at the 0?
Okay.
Right. If we said, what if the Hessian of it was Dirac delta times some matrix? What would that look like? And then we did all the algebra with that. And sure enough, it behaved quite well. And so yeah, then you solve everything, and then you take the limit as the singular value, or as the points go to 0, and everything was working. And so we were like, well, this should be formalizable, and this was the best formalization we came up with. Chris? Yeah, so it basically has to do with the exchangeability assumption. So cross-validation depends on that exchangeability assumption. And so without that exchangeability assumption, we end up with cross-validation not Cross Sorry, give me a second. Cross-validation without the exchangeability assumption is totally biased, and we don't have any guarantees on it. The kind of intuitive explanation that Emmanuel once used to describe it to me was, if you picture an image, why would you expect the pixels over here to be exchangeable with the pixels over here? And that's the rough kind of summary for why that falls out that way.
Great, so as chair, I think I should say thank you on the call. Thank you. I will ask the audience to close that.
Thank you. Thank you.